Okay, thanks a lot for the organizers for the invitation. So I'll be trying to speak to you about what we call correlated Gromov-Witten invariants. Or maybe the name is not terrific, but it's the less worse combination we could think about. So what does it mean? It's a refinement of some relative Gromov-Witten invariants, which maybe is more well known. Then why not refine Gromov-Witten invariants? It's because refine is already taken, unfortunately, and not really what you expect. So I'll come back to the correlated later. So what is the setting? We consider X a projective variety on smooth. With, and this will come in a moment, positive what's called irregularity. I pick L a degree 0 line bundle over X. And I consider the projective completion of L, so meaning the total space of L plus O, which contains two specific divisors, which are the 0 section and the infinity section. So this is the general setting. Yes. Okay. Basically, for almost the whole talk, you may always imagine that X is an elliptic curve. So meaning basically the simplest variety with a positive H10. And L is a trivial bundle. Meaning, in fact, my variety Y is a surface, and it's in fact just E cross P1, which contains E cross 0 and E cross infinity. Okay. Then what do I mean by relative invariance? So I will consider the moduli space of stable maps relative to, so let's call this divisor D plus or minus, according to if it's 0 and infinity. So for that, I need to fix a bunch of data. I'll fix G a genus. But then I will also complain. Okay, G genus, N, M positive integers. Beta an homology class inside X. And I think, and W, which is a family indexed by 1 to N, with sum is equal to 0. Then my modular space is M, G, M of Y relative to my two divisors, I fix beta and W, which is a set of maps from some a curve C, which may have, so it's a nodal curve with some genus on its component, some more points to Y, such that, what do I wish? When you project to X, you get some curve in X. I wish for its degree to be exactly beta. The genus of the domain is exactly G. And the n more points are mapped to or g plus or minus according to whether the sign of W is positive or negative. Meaning I have, if it's positive, it's mapped to infinity. If it's negative, it's mapped to 0. And with which intersection order exactly the absolute value of W. So with order Wi, and I have m additional more points. Okay, so for instance, if I go back to my favorite example, in case x is an elliptic curve, then I may draw my E cross P1. In this case, then beta is the degree of the cover. So I have a map into E cross P1. So I can project to the elliptic curve. I get a cover of some degree. So meaning the homology class is in fact an integer multiple of the fundamental class of the elliptic curve. Here I chose n to be 5 because I have 5 points mapped to the boundary. So I have to choose some weights also. So for instance, I don't know, 6, and 4 to 6. And I put minus to say that these points are mapped to the 0 divisor. 6 and 6 are positive, so it's mapped to the infinity divisor. And the absolute value are the tangency orders with the corresponding divisors. So W here is -4, -2, -6, 6, and 6. Which time am I forgetting? I have one additional mark points here. So M is equal to 1. And the genus is, so I put 2 holes, so it's 2. Okay, it has some dimension. With a formula, which is, I won't give you the general case, but in this case, it's equal to n plus m plus g minus 1. Okay. It is endowed with 2 features. Yes. Yeah, you add the genus of the components plus the genus of the dual graph. When I said this space is of dimension this guy, it's slightly wrong. In fact, it may have several components of various dimensions, but we expect this dimension, and in fact, we can construct a virtual fundamental class which is exactly of this dimension. So you may imagine this is not a manifold. If it were, it would have a concrete fundamental class. It's not, but we have a class playing the same role, which will be useful in a moment. So this is the first thing we have. Second, we have an evaluation map. Which starts from a moduli space, so MGM, Y, D plus or minus W, which for later I will just write M, assuming every data is fixed. And it lends into X power N, Y power M. And what does it do? If I am given a map from C to Y, I just look at where are my mark points sent. So I said I have 2 types of mark points. I have the ones indexed by M, which are mapped to somewhere inside Y. So this is why I get a part into YM. So this belongs to Y. And I have my mark points, which are mapped to the boundary divisors, the d plus or minus, which are the 0 and infinity section. And these two divisors, their projection are identified with x. So that's why I get a part into xn. So projection to x. Okay. And then we define relative Gromov-Witten invariants. Formally as intersection with the virtual fundamental class. I will denote it like this. Of the pullback of a cohomology class of the target space. What does it mean? In fact, you can pick a product of cohomology classes here, corresponding to Poincare dual class to some cycles, like for instance, Poincare dual to points. And then when you pull back, it amounts to fixed conditions on your curves to pass through some fixed points, for instance. So let's do an example right now on the computation. Yes. Condition on what? No, not yet. Be patient. Yeah, exactly. Whatever is the base. Do not push me to go faster. Okay, so let's compute. What I will denote like this. Alors 1, A times E. So see in our favorite example, E cross P1. And yeah. Now, what does it mean? It's partially a concrete example because I choose beta to be basically anything. The genus is 1. M is also equal to 1. W is any guy. And so N is also anything. And what does this guy mean? It means exactly I pulled back a point constraint for boundary points except the first one. And a point condition for the unique interior mark point. Let's draw my picture, which will be basically the same. So now the genus is 1. So I'm looking for genus 1 curve mapped to E cross P1. I fix the position of every boundary point, like its projection to X, except one of them. And I also fixed the position of one intermark point. Now then you can check that the dimension is to, I chose M and G to be 1, so I get N plus 1. And it also matches exactly the rank of the constraint I imposed because points are dimension 1 for the one on the boundary, of which I have N minus 1. And a point inside is imposes the codimension 2 constraint. So I should add 2, and these two are actually equal. So if I impose this constraint, I expect a finite number of curves, which will be encompassed in this Gromov-Witten invariant. What is the value? Should make some room on the left. Because it turns out, in this case, we can make an explicit computation, basically, without also knowing what is the virtual fundamental class. Uh, 2.0, 1W1. Genus 1, I times the class of the curves on this W. Now this is equal to A n minus 1. I should not write this one first. And the last one is W1 squared. What is sigma 1 of A? This, by definition, is the sum of divisors. And how does it appear? Because choosing a map landing inside E cross P1, in fact, when you project, you get some cover of the base elliptic curve. A cover of degree A, and you probably know there is exactly sum of divisors of A covers of C2A. So this is the choice of a cover. This is the bad name. E from C to E, where C is an elliptic curve. Okay, this is for okay, sigma of A. And it becomes also, it's a group homomorphism. If chosen base point. Okay, so now I have my map to E cross P1. No, sorry, only to E. And then where does the second factor comes? So once I have my factor, I need to find where are my mark points. But the image, the projection is fixed. But since I get a degree A cover, it means I have exactly A preimages for each of them. So for I between 2 and n mark points, I have A possible preimages. So this gives me my A power n minus 1. And then where does the last factor come from? Because technically, the last mark point is free. But to find your map in not only to E, but in E cross P1, you should find a meromorphic function on your elliptic curve C. So find a meromorphic function phi from C to P1 with chosen divisor, a fixed divisor. What is divisor? It's exactly the points mapped to the monary with the tangency order prescribed by my data W. And you probably know that this imposes a condition on the relative position of the mark points. We should have in C sum from 1 to n of Wi Pi equal to 0. And this is because I consider the sum inside C, which is a group. So meaning this can be rewritten as W1 P1 plus sum from 2 to n, Wi Pi. These guys have been chosen in the second step. So now I'm just looking for the position of P1, and P1 is determined by this equation up to W1 portion, of which there are W1 square elements. So that's why I get W1 square. Okay, so for now, still no refinement, but it will appear just right now, once I make room for continuing. Okay, so observation. Since this map is a group morphism, I can push this relation living inside C to a relation inside E. So previously, I had the sum of Wi pi equal to 0. So I still get sum of Wi f of pi with projection, which is 0, but now inside E. Meaning there is a relation between the points in which I intersect the divisors. If you assume that there exists a common divisor to the Wi, like easiest case is like assume they are all 2 or -2. Then instead of considering the linear combination with coefficients Wi, you may just divide by this common divisor. Of pi. Then it's not necessarily 0 anymore. But we know that when you multiply by delta, it needs to be 0. So it's some torsion element. Okay, so theorem. What does it mean? It means, in fact, the moduli space of curves is far from being connected because we found a map to a disconnected space, the discrete space of torsion, possible torsion elements. So it gives you a way to split the moduli space into different components. And it tells you some relation between the possible images of the mark points at infinity. So they are not chosen independently because they may satisfy this being equal to some torsion elements which you may pick. For now, you do not know. Maybe there's still only one possibility, and in fact, the components are empty for most choices of torsion elements. It's not the case, as you will see later. And so since the points are not chosen independently, they are correlated. So that's why we get correlated stuff. So theorem, in fact, this is not specific to the elliptic curve, although it's easier to present in the elliptic case. And so I will try to present the general version now. It's kind of informal theorem. So if you have a common divisor, so now it's back to the general setting of y being a projective bundle over base x. The virtual class splits as a sum indexed by elements of tor delta, donc still torsion, but now it's under the delta torsion elements of the Albanese variety, because now X has no reason to be a group anymore. Okay, and now my plan is first, why should we care? Then present the Albanese variety. Albanese. Then get an example, and we'll see if I manage to finish that already. Any question up to this point? Sorry? Yeah, in general, it will be indexed by a torsor. In this case, we get the trivial torsor, which is the group itself, because I chose the line bundle to be the trivial bundle. If you deform it to be another one, then basically I'll raise it. The relation being, it's not equal to 0 anymore, it's equal to something. You get roots of this something. Yeah, it won't be the same. Like, yeah, you may expect like 2 extremal cases, only one contributes. So in fact, we do not get a refinement. Or it's equally spread, meaning it's not really interesting. We may get both. Okay, so motivation. Now, why should we care? First reason is because it's there, so why not study it? Second reason is if you care about invariance for abelian surfaces. So most easiest example of abelian surface is a product of elliptic curve. And one common feature, standard feature to understand curves into E cross F is to degenerate E cross F to some easier surface with some singularities. To E cross to degenerate F to a nodal elliptic curve, which is basically then E cross P1. And then you identify both divisors. Let's take the then when you look for curves in the central fiber of this degeneration, you should look for curves that intersect the boundary divisors, but recall that the two are identified. So when it meets the top divisors, it should also meet the bottom divisors at the same point with the same tangency order. So easiest case when there is just one. And then what we do is basically degeneration formula tells you to understand curves in abelian surface, I should understand curves inside here with matching conditions. And to do that, usually we just intersect with the diagonal to force the points to agree. The problem is that points here almost already agree, because if we were to intersect with the diagonal, this condition should be transversal. And here it's not, because if we have already the 2 points, the relation I told you before inside E cross P1 tells me that my 2 points, P1 and P2, they already agree up to torsion. And if W was 1, they automatically already agree. So I do not have to intersect with the diagonal. But now, if W is non-zero, like let's say 2, I get that these 2 points agree up to 2 torsion. But I need them already to agree exactly. So meaning I should just pick the component of the generalized space where they exactly agree, not the part where they differ by some non-zero 2 torsion element. So in fact, this refinement already appears here when we try to consider invariance for abelian surfaces. It also appears for, I won't talk about it, for bielliptic surfaces. Well, now it's basically the same, but the fiber 2 divisors are identified by non-trivial automorphism. So meaning it's important if you wish to understand invariance for abelian surfaces to understand this invariance for E cross P1. All good? Okay, so if the base is not an elliptic curve, why does what I did make sense? because I consider the sum of the points. But if X is not a group, I cannot really add the points. So for that, we can consider the Albanese variety. So what is it? So go back to the general setting where X is a projective variety. And then above X, you may view it as a Jacobian for X. Jacobian, you know, for a curve. X is not necessarily a curve. It will be its Jacobian if X is a curve, but it's like a generalization, if you wish. How is it defined? Most explicit definition is you take the dual of the space of holomorphic one form and you quotient by the lattice of one cycles. Why is this guy living inside this guy? Just because if you have a one cycle, you may integrate an holomorphic one form over this one cycle. And it does not depend on the representative of the one cycle you chose. So this is a complex torus. What's nice is that you get from that directly a map from X to above X, which is, as you might imagine, basically the same as in the case of curves. If you pick a point X inside X, then you should define basically an element of the dual of holomorphic one form. So let's X0 be a base point. Then you map a holomorphic one form to its integral over a path from X0 to X. This a priori is not well defined because it may much depend on the path you chose between the 2 points. But if you pick 2 different paths, they will differ by 1 cycle. So it's well defined once you quotient by the integrals over 1 cycles. So this is well defined. Modulo H1 of X Z. So now I'm kind of happy because in the elliptic setting, I could already sum up points because my elliptic curve was already a group. Now, even if X is not a group, I may add points. It's just that now I land into the Albanese variety instead of X. Okay. Then the Albanese variety satisfies a bunch of interesting properties. Like first, it's universal for maps to abelian varieties. Meaning if you have a map from X to A, an abelian variety, there is a unique map which will be a group morphism between the two, between above X and A. Using that, it's also functorial in X, meaning if you have a map between X and X prime, you get a group morphism between the two Albanese varieties that commutes to the map between the varieties and their Albanese. And last, even if you are not accustomed to the Albanese variety is in fact the dual of the Picard group. The Picard group is a group of line bundles. So in fact, it may also be described with this Hodge interpretation, if I might say. So H1 of XO quotiented by the cohomology with Z coefficients. And then, in fact, this F star is just the dual to the pullback, so it's F upper star, upper star. And this way, you get also a family versions. Because with this definition, it's not really clear if you deform your variety X, what happens with Albanese variety. But you know that you can deform the Picard group. So then you can also deform the Picard of the Picard, which is the Albanese variety. Yes. Depends on what, sorry? Yes. In fact, only up to translation. Because if you have a morphism between X and above X, you may get many just by composing with the translation. Okay, any question? So now that we are experts in the Albanese variety, I will use it to redescribe the refinement. Okay. Okay, so recall I have my variation map. So meaning this is the space of the curves I consider. Then I consider the image of the mark points mapped to the boundary divisors. And in the elliptic case, I consider their sum with some coefficients. So now I may just do the same. So sum of Wi xi, except now if I cannot remake the sum of elements in X, but I can if I land into the Albanese variety. So now is image inside above X. Okay, and this global composition I will call kappa. Now the claim is that kappa is constant. What happened in the elliptic case? If I consider a curve, I look at where the mark points are mapped. I do this combination. Then the image is always the same. So its image only depends on the homology class beta and L the line bundle, which was used to construct the projective completion Y. Okay, then I have two things to say. Why is it constant, and what is the image? It's a little bit easier to explain when the domain is smooth. So let's consider f from C to X with C smooth. And in fact, as in the elliptic setting, enhancing the map from C to X to a map to Y is exactly choosing a section of the pullback of L to C. So previously, it was the pullback of the trivial bundle, which is already trivial. And then we should find a section with prescribed poles and zeros. So we should have this condition. It's a little bit more complicated to express when C is not smooth, but let me keep a smooth domain for now. Okay. So I have, let's start with pick 0 of C, which in this case is also the Albanese variety of C, which is exactly is Jacobian. For curves, you know it. Then, since I have a map from C to X, I have a map between the Albanese variety. Just I push forward my points. So I land into alb of X. It maps P minus P0 to, maybe I should use colors. F of P minus F of P0. Inside the formal sum inside the Albanese variety. And this guy corresponds to, in fact, the line bundle with divisors P minus P0. Okay, then what is the image of this line bundle? So O of sum of Wi Pi. It's mapped exactly to my quantity I wish to consider, the sum of Wi F of Pi. Okay, is everything good? Now I may use my hypothesis that this line bundle is actually the pullback of L, which comes then from pick 0 of X. And to L is mapped to its pullback. So in fact, the image by the big kappa is in fact the push for it's kind of push forward of pullback of L. And this way, it's not clear, it does not depend on F because F is here. Okay, then I should understand what is this composition, because what I do basically is I have my line bundle over X, I pull it back to C, I choose a section with some prescribed poles and zeros, and then I evaluate their position. In fact, this sequence, so between complex tori, it's induced by the pullback and push forward between, where is it written, these Hodge groups. Basically, I have H1 of X to X. I pull back to H1 of C O C, which is in fact the dual to H0 of C omega 1 of C. And this is by Serre duality or Poincare duality, depending on how you see it. And then I push forward to H0 of X omega 1 of X. Dual. This is a composition of maps between vector spaces. And then you just quotient by the corresponding lattices. So here the cohomology with the coefficients, same here, and here the one cycles. As I get a map from one space to the dual of another, in fact, it corresponds to some bilinear map. What is this bilinear map? So I should get 0, 1 form and the 1, 0 form. Basically, it tells me I pull back and this is a dual to the pullback, so it's also a pullback. And then I should integrate over the curve C. I integrate over C, the pullback of alpha and the pullback of omega. And then I just get out of the pullback, and this is equal to the integral over f of C of alpha wedge beta, wedge omega. Why does it not work? So in fact, written like this, it only depends on the homology class of the curve, not on f anymore. My kappa is constant, and its image I will denote by phi beta of L. And if I have beta, I get a morphism from this guy to this guy, quotient by the lattices. And then L is exactly an element inside P0 of X, so I map it to the Albanese variety. In the example, of the elliptic curve, I have a map, and the degree was A times the fundamental class of E. As E is already a group, in fact, it is equal to its Picard variety, Picard group and Albanese variety. In fact, this morphism is just the multiplication by A. Okay. In particular, if you pick the trivial line bundle, then the image of 0 is 0, so we get back to our relation that the sum of the images in E cross P1 should be 0. If the line bundle is not trivial anymore, you just get some other guy, which is A times the class of the line bundle you chose on the elliptic curve. Okay. Then when the WRs are not co-prime, you have a common divisor. Then we just consider the same map, but you divide the images by, what is it, by WI. We start from the same moduli space. It turns into the Albanese variety. And then you make the sum of WI over delta of the f of pi. And now this lens has value in the delta roots of phi beta of L, which I'll denote by T delta of L beta. And this guy is a torsor under the torsion group. T delta of So these elements we call correlators because they give a refined information on the relative position of the points where my curve meets the boundary. Like there sum is equal to some elements in this torsor. Only a finite possible values are allowed. Okay. Then we can consider basically if theta is a correlator, then we can consider n theta, which is basically the pre-image of theta inside the moduli space, then you get that M is a disjoint union of M thetas. And we recover what I told you at the beginning. The moduli space M is very much not connected. One way to split into different components is to consider the image by this discrete map, giving me information on the relative position on the points. Then you get that the virtual fundamental class splits as a sum of classes restricted to these components. And you get what we call correlated invariants just by intersecting as before pullback of cohomology classes, but now with on these restricted virtual classes instead of just the big ones. How do we, so now it's indexed by z theta, which belongs to torsor. Okay, so definition, I think we're good. Now the problem is, can we compute some values? More important, do we get non-trivial values? So now I think until the end, if I get sufficiently much time, I will give you what's the value of the refinement of the only invariant I computed so far, which is elliptic case, one interior mark point, and genus 1. For example, so still elliptic curve. L is a trivial line bundle. What do G is equal to M is equal to 1, W fixed. To recall, the values was sigma of A times n minus 1 times W1 square. And this guy is sum of the divisors. To give you the result, I will need somehow a twisted divisor function. To set sigma delta of A to be sum of divisors of A over delta if delta divides A and 0 else. And for instance, if delta is equal to 2, then just divide A by 2 when it's possible and make the sum of divisor. If it's not, then you get 0. If delta is equal to 2, as we are in the case of L is a trivial line bundle, what is the possible values of the correlator? Which theta may I pick? We said it's a delta root of the image by this phi beta, and in this case, it's just 0. So theta is a two torsion element. Then if you pick a representation of the elliptic curve as C modulo 1 and tau, you may represent the torsion elements by 0, which is a special one, and the other 3. And then the values of the refined invariants, with one interior points, one free points. Is equal to, in fact, we have two parts that remain. You still have this A n minus 1, W1 square, And that, in fact, this sigma is replaced by different possibilities according to what is the value of the torsion elements. What is it? 1/4 of sigma of A plus 3 sigma 2 of A. And for all the other ones, sigma of A minus sigma 2 of A. I will comment in a moment. So it's the easiest possible computation you may do because delta is the smallest possible. And it is in the easiest example you may consider. Slightly more complicated is if you take delta is equal to P. Then we also have a special torsion element, which is 0, for which the value will be sigma plus sigma bar P times P squared minus 1. And for all the other one, sigma minus sigma bar P, 1 over P squared. Just we have a generalization for prime numbers. We can also give an explicit formula for basically every delta, but it would give me get me too far away. What can I say? It's really a refinement because now if I unrefine, basically I make the sum of all the possibilities. How many sigma do I have? 1, 2, 3, 4. Divided by 4, I get 1, which was the result here. And now the sigma bar 2 disappears because I have minus 1, minus 1, minus 1, and I have 3 here's. The same here because I have P squared minus 1 minus sigma P, and I have P squared minus 1 here. So it's really a refinement. It also tells me that it does not split evenly because the result is not the same. Always no, because if A is odd, then sigma bar 2 of A is 0. So you may forget about all this sigma bar 2, and you get the same contribution in every possible value of the correlator. But if A is even, it does not split evenly. Is it surprising? No, because if you recall, here, delta theta is equal to 0. It's because I chose the line bundle to be trivial. So I get equal to 0. If L is non-trivial, then the relation is delta theta should be equal to, I said, the image of the morphism, the image of L by the morphism from peak 0x to L above x, which was multiplication by A. So I should get equal to AL, where L belongs to E, which is seen as the Picard group of E. Because in E, all of them coincide. So here, delta is equal to 2, so even it's like that. When I divide by 2, if this guy plays a specific role, it means there should be a preferred root of AL. If A is even, there is. You may just pick A over 2L. If A is odd, there is apparently no preferred root of AL because A is not divisible by 2. And in that case, in fact, it's reflected by the fact that all the contributions are the same because there is no preferred root, so everything splits evenly. But if not, you get an interesting refinement. To finish, what may I say? This is, of course, not a proof. It's just an interpretation of why should they be the same if A is odd? Because we have no preferred root. You can, in fact, show that using monodromy inside the Picard group. You can show that, in fact, these invariants are, we are still right to call them Gromov-Witten invariants because they're deformation invariants. If you move a little bit If you deform a little bit the line bundle on the base, then of course you deform a little bit the correlators. Like now it does not satisfy equal 0, for instance, here, but it's equal to something else. But the coefficients in front of them vary continuously, but there are integers here, so they are constant. They do not move. So we still get invariance, deformation invariance, and we can get computation basically in 4-point insertions in the E cross P1 case. So any line bundle over any curve, over any elliptic curve. I think it's a good place to stop.